Welcome to this explainer. Today, we're demystifying distance vector routing protocols. If you're already in the networking space, you know how crucial routing is, but we're going to break down the actual mechanics here. We'll keep it super clear, highly structured, and get right to the point.
Okay, to really visualize this, imagine a pre-GPS world. You're driving in a city, right? No map on your dash, no bird's eye view, absolutely no smartphone. All you have is the very next intersection and a guy standing on the corner telling you exactly how many blocks away your final destination is. You don't know the whole route, just the next step and the total distance. Well, that is exactly what a router experiences in the dark on a network. It's literally the perfect way to visualize how these protocols actually function.
So at its core, distance vector routing is all about, you guessed it, distance. Specifically, the number of hops to reach a destination network. Think of it like neighbors hanging out in their backyards, just constantly shouting over the fence to tell each other about the best routes they know. They do this by periodically swapping their entire routing tables with adjacent neighbors. And to make their decisions, they rely on specific metrics. That could be a simple hop count or something a bit more complex, like bandwidth or delay. Here's our roadmap for this explainer. First, the distance vector concept. Second, meet the protocols. Third, key network characteristics. And finally, the modern routing landscape. All right, section 1, the distance vector concept. Let's look at exactly how this works in practice. It really is a brilliant word-of-mouth mechanism. First, a router identifies its direct, immediate neighbors. Then, on a really strict schedule, it periodically hands over its entire routing table to those neighbors. Finally, it takes the new info it just got back and makes routing decisions based on its chosen metric. They literally just swap lists with the router next door and pick the easiest path. It's a highly localized, step-by-step way to map out a massive network.
Moving right along to section 2, meet the protocols. We're going to look at RIP, IGRP, EIGRP, and HROT.
Let's look at the evolution between two of the foundational ones. On one side, you've got RIP, the Routing Information Protocol. It's one of the oldest and simplest distance vector protocols out there. It's basically the neighbor who only cares about counting hops. Fewer hops, better route. It's great for smaller networks, but honestly, it converges pretty slowly. They did roll out version 2 to support things like subnetting, which was nice, but then on the other side, we have IGRP, Cisco's Interior Gateway Routing Protocol. This one's the sophisticated neighbor. Instead of just counting hops, IGRP actually factors in the road quality. We're talking bandwidth, delay, reliability, and load. Because of that, it handles larger networks and converges way faster than RIP. But evolution didn't stop there. As networks got faster and more demanding, we got EIGRP, Enhanced Interior Gateway Routing Protocol. This is an advanced proprietary Cisco protocol that basically acts like a hybrid. It takes the absolute best of both worlds, balancing the easy setup of a distance vector protocol with the accuracy and rapid convergence you'd normally only get from link state protocols. It uses a really powerful composite metric, again, looking at bandwidth, delay, reliability, and load, and it seamlessly handles both IP and IPv6. Now, just to round out the family, we should also mention HROUT. It's a very simple distance vector protocol, but it's really only used in specific niche networks. You're definitely not going to encounter it as often as the big players like RIP or EIGRP, but it's a great reminder that these specialized variations absolutely do exist out in the wild. Let's jump into section 3, key network characteristics. It's time to weigh the pros and cons. A massive factor here is convergence time. That's just the time it takes for routers to update their tables after the network topology changes. Think about our driving analogy from earlier. When a major road closes downtown, how long does it take for the entire city to find out and actually adjust their routes? Because distance vector relies entirely on that neighbor-to-neighbor word-of-mouth system, convergence can honestly be quite a bit slower compared to link state protocols. So, weighing it all out, on the plus side, they are wonderfully simple to configure. If you're running a small or medium-sized network with a basic topology, RIP is an incredibly easy out-of-the-box fix. But the drawbacks are real. Aside from that slower convergence time we just talked about, there's a ton of constant network overhead. Remember those periodic updates? The routers are constantly sending massive tables back and forth on a timer. It's like neighbors screaming over the fence, even when literally nothing has changed. It eats up incredibly valuable network resources. And then there's the fatal flaw you absolutely have to watch out for, the count to infinity problem. Since routers only know what their direct neighbors tell them, if one neighbor gets a bad piece of routing info, they pass it on. Then the next neighbor passes it back. And suddenly, the whole neighborhood is repeating the exact same bad information in an endless loop.
The hop count just keeps ticking up towards infinity, and your data packet goes absolutely nowhere.
All right, Section 4, the modern routing landscape. Where exactly do these protocols fit in today?
Just to cement everything we've talked about, you can map the simple hop counters like RIP directly to smaller medium networks. Step up to the more advanced IGRP and you're perfectly covered for larger networks. Step up once more to EIGRP, and that composite hybrid metric of bandwidth delay and load positions it perfectly for modern rapid network environments using IP and IPv6.
So, to wrap up this explainer, I want to leave you with this thought. Distance vector protocols laid the absolute groundwork for how we connect, and they are definitely still used today. But as our networks have grown vastly more complex, the landscape has fundamentally shifted. Do modern, massive networks rely more on link state protocols like OSPF for their internal routing, or BGP to keep the broader global internet moving? Understanding distance vector is the key to unlocking how we got here, and more importantly, where networking is heading next.